Alright guys, so we're moving on to our next section where we're talking about real numbers and the number line. So you'll want to pause and copy down these vocab words. First one is a square root. A number is a square root of a number if if a squared equals b. Okay, so any number that has a way where you could divide it by a number and get that same number, I know that sounds weird, that is what a square root is. So an example of this, probably an easier way to understand it, would be 7 squared equals 49, so that 7 would be the square root of 49. If you divide 49 by 7, you get 7. That makes it a square root. This little check mark looking symbol right here is called a radical symbol. The expression under that radical symbol is called a radicand. We're going to do more work with this later in the year, and I will use those vocabulary terms. I'd like you to get in the habit of also using those vocabulary terms. The whole thing together is called a radical. That's not radical like awesome dude. That's just what it's called in math. I have no idea why it's called that, but that is what it's called. Alright. Okay, so something that's going to be really important and helpful for you moving forward is to know your perfect squares. So here you'll want to pause and copy all of these down, and you want to commit them to memory. A lot of them you should already know, because they are related to your basic math facts. But the ones that students sometimes don't know are these larger ones, like the square root of 169 or 196 or 225. You could go up even farther. I think that's a good starting point. So we're going to go with that. So please have those memorized. It will make your life easier. Alright, so simplifying square root expressions. What is the simplified form of each expression? This is pretty simple. First of all, you got to think what number, when multiplied by itself, equals 81. So in this instance, if you know your multiplication facts, you know very easily and very quickly that that's 9. This one, we're going to talk about the rules of what you do with a fraction under a radical symbol. We'll talk about it in more detail, but for now, just know that this radical symbol kind of distributes to both the numerator and the denominator, so that this is the same thing as radical 9 over radical 16, which is how you would say that. You'd say the radical and then the number that's underneath it. Well, here now we have a problem that we can do. The square root of 9 is 3, and the square root of 16 is 4. So that this is equivalent to 3/4. So here are a couple problems for you to try. I want you to pause the video and try them. And hopefully after you're finished, you find that this one is 8 and that this is 1/6. Alright, if you did not find those, try to figure out why. Let's keep moving here. Okay, so estimating a square root. Here we have a word problem. It says lobster eyes are made of tiny square regions. Under a microscope, the surface of the eye looks like graph paper. A scientist measures the area of one of the squares to be 386 square microns. What is the approximate side length of the square to the nearest micron? So the first thing that you need to think about is we are talking about squares. Alright, so if I have a square, and that's not straightest looking square, but if I have that, if I want to find the area of that particular square, remember I take one side length and I square it, because I know that the side length of all of these sides are exactly the same. So the area of the square can be found with A equals S squared. A equals S squared. So I take this value and I'd substitute that in for the area. So I have 386 equals S squared. I need to find the square root of that. Now it tells you here what is the approximate side length of that to the nearest micron. So in other words, I'm looking to the nearest whole number. There are a couple ways to do this. One way is you could put this into your calculator, 386, find the square root of that, and then very quickly round that to the appropriate way. But what if you don't have a calculator? So that's what I'm going to go over with you here is what do you do if you don't have a calculator? So the best way to do this would be to start listing your perfect squares. Okay, so we stopped at 15 on that other slide, and we know that that 15 squared is equal to 225. So we're going to keep going up on that and look for perfect squares that are around 386. So 16 squared will give us 256. That's too small, and it's not even really all that close. So I'm going to go ahead and skip, and I'm going to try 18 squared. And 18 squared is equal to 324. So that's getting closer, but it's not quite there. Let's see what 19 squared is. 19 squared is 361, and that's not quite there either. So we'll try 20 squared, and that is 400. All right, so at that point, we go over 386. 386 has to be somewhere in between 361 and 400. Therefore, its square root, or the side length of this square, is going to be somewhere between 19 and 20. Now, the way to figure out which one do I want to use 19 or do I want to use 20, is think about, well, what is 386 closer to? 386 has a difference of 14 to 400. And between 361, it has a difference of 25. So 14 is the smaller number. So if I were making an approximation, it's closer to the 20 squared value. So I'd say about 20 microns. So you find where that would fit in between the perfect squares. That's how you would estimate that, or to give an approximation. Okay, so here's some more vocab words. Pause and write these down. We're not going to use these vocabulary words a lot. I just want you to be familiar with them in case I say them when I'm speaking. So a set is a well-defined collection of objects. Each object is called an element of a set. So if you have a set and it was something like 1, 2, and 3, a very small set, that is my set. It's a well-defined collection, and each one of these things is called an element. So 1 is an element, 2 is an element, 3 is an element. A subset of a set are elements from the given set. Okay, so I could say a subset of 1, 2, and 3 would be just 2 and 3. That is what a subset is. A rational number is any number you could write in the form of a over b, where a and b are integers and b can't equal zeros. Okay, rational numbers as a decimal, they either terminate or they repeat. And these are things that you cover in pre-algebra in 7th grade, so hopefully this is not new to you. I want you to associate fractions with rational numbers. If it can be written as a fraction, then it is a rational number. So here are some sets of numbers. You need to pause and copy these down. The natural numbers start at 1 and count up by 1 indefinitely. So 1, 2, 3, and so on. I think they're called natural because they're numbers you could actually have. You can't have 0 or something. You would just have nothing. Whole numbers are all of the natural numbers except we add this 0 to it. And then the integers are all of the whole numbers, and then the opposites. So the opposite of 1 is -1, the opposite of 2 is -2, and so on. An irrational number cannot be represented as the quotient of two integers. In other words, you cannot write it as a fraction. In decimal form, irrational numbers do not terminate and they do not repeat. Common examples of this would be something like pi. I know all of you are probably familiar with the number pi. Also, radical 3 would be an example of one. If you were to put that in your calculator, you get a decimal that goes on forever. It doesn't terminate, but there is no distinguishable pattern that repeats. Okay, so here's a Venn diagram breaking this down. I want you to copy this down into your notebook, so make sure you pause and do that. But you'll see here we have all of these things are called the real numbers. Now you may be saying to yourself, that's kind of a weird name. Something that you will learn about in Algebra 2 is called imaginary numbers. So there actually are numbers that are not real numbers. Kind of like an imaginary friend, except actually legitimate. So here under real numbers we have rational numbers and we have irrational numbers. Notice here that there's a line separating these two. There are no numbers that are both irrational and rational. It's either one or the other. Within the rational numbers we have those other sets that we are looking at. These are subsets of rational numbers. So the natural numbers, 1, 2, 3, and so on. Notice that this is included, and you may have thought, well, there's a radical. How can that be? Well, radical 25 would simplify to 5. So that makes it a natural number. 4 over 2 would simplify to 2. So that makes it a natural number. You add the whole numbers, and notice there's only one number that exists that's a whole number, that's not a natural number, so this 0 is over here all by itself and lonely. The integers include all the whole numbers and all the rational numbers, but then you throw in the negative numbers. Now this, just like we were looking at over here, would simplify to -2. This would simplify to -4, so that's why that's included. And then all these numbers are ones that can be represented as a fraction. Okay, so this, for instance, is the same thing as 1/2. This is the same thing as 1/3. Both representations of that number as a fraction, even though in this state they don't look like a fraction. Over here, it's all these weird things that repeat. We already mentioned pi. We have a radical 10, negative radical 123. This has a pattern, this 0.10100100001, but it is not a specific set of numbers that repeat itself. So that's why that is considered an irrational number. So when you're classifying numbers, you start at the most specific one that you could get and you work your way out. So this 15 right here, we could classify as natural. And if it's natural, it's automatically a whole number. And if it's a whole number, it's automatically an integer. And if it's an integer, it's automatically rational. So you would work your way out on that Venn diagram that you copied down. This one right here, it's a terminating decimal, so it's rational. And that's the only thing that it is. This is not a perfect square, so this would be an irrational number. So here we're going to talk a little bit about inequalities. These are useful when you're comparing values, so pause and copy this down. Remember, the alligator eats the bigger value. Another way that I remember these is that less than kind of looks like an L, and less than or equal to kind of looks like an L. You should be familiar with those, but make sure you have them copied in your notebook. Here, what is the order of these values? The easiest way to do this is to convert everything to decimal form. So the square root of 4 is 2. 4/10 is already a decimal. -2/3 is the same thing as -6 repeating. Radical 2 is equal to 1.41. And then our last one, -1.5, is already in decimal form. And from here, you would want to order these. Okay, so this is my smallest because it's the farthest to the left on a number line. You're asked to order this on a number line. So we'll go ahead and create the number line. And there we go. So we'll call this -2, -1, 0, 1, and 2. And when you order this on the number line, I want you to get in the habit of using the original values. So -1.5 would go right here, and I'm going to write that value above it. The 1.41 is going to go almost halfway, but not quite. But instead of writing that, I'm going to write radical 2. -2/3 is going to be close to here. 0.4 is just 0.4, or 4/10. And then this last one, radical 4, would go right here. So now they're in order. You could write them out in order like that. They're also in order on the number line. And I believe that's it for this lesson. Yep, let me check. So that's it. I'll see you in class, and I hope you took good notes.